a little faster, and boom, there it is. Welcome back to Cloud 42. I'm James. Well, today we are back on the Electronic Leadscrew project to address a small issue that was reported by one of you. If you're not familiar with the Electronic Leadscrew, it is an open source, open hardware project that allows you to replace the change gears on a metalworking lathe with an electronic controller and a motor so that you can change feed rates and thread pitches by pressing buttons instead of changing gears. Now, there will be a link down in the video description to the GitHub project that has the source code and links to all of the hardware that you would need to install one on your lathe, and also a playlist for the video series. I think this is part 20. I've got a whole video series on the Electronic Leadscrew starting from the original concept all the way through development and actually manufacturing of the part. So if you're interested, go check that out. This is the Electronic Leadscrew install on my Grizzly Geo602 lathe, and there's basically two things that happen mechanically. You note that the change gears that normally connect the spindle down to the lead screw input shaft are gone, and they've been replaced by an encoder, which is driven by a belt off of the first idler gear from the spindle, and a servo motor that drives the input to the shaft here. So if I set this up, now I have a 12 thread per inch lead screw, so I will set this up to thread at 12 TPI, so the lead screw should move at exactly the same rate as the spindle. So if I just grab the spindle here and turn it around, you can see that one full revolution of the spindle results in one full revolution of the lead screw. And if I just start this slowly, you can see that running, and as I increase the pitch of the thread, all the way up to 80 threads per inch, this slows down, and if I pitch it all the way down to 8 threads per inch, it speeds up. And then of course we can switch this over for feed, so if I want to feed 5 thou per revolution, you can see it moves quite slowly compared to the spindle. Now this, honestly, is still the temporary install that I did until I got around to doing this permanently. I just have a little Popeye magnet that with a 3D printed part that's holding the encoder in place. I will eventually get around to machining an aluminum part and screwing it into the mill, and then down here I've got the banjo that's normally used to hold the change gears, just coming out forward with a little bracket to hold the servo off the front with a belt. Now eventually this servo is going to go back, there's space above the motor back here, and I'll modify this back plate and fit it back in there, and maybe we'll get to that soon, but honestly, it's just been working, so I've just been using it. Now the problem that was reported is something that happens when you spin this up at very high pitches, so like a 4 or a 6 millimeter per revolution thread or 8 threads per inch, and you run the lathe very, very fast, like 3,000 RPM. It's not something that I can do on this machine. This machine will not actually reach the speeds necessary to demonstrate the issue, but I have a test bed that I use for testing arbitrary configurations, and we can demonstrate it on that. Let's go in the office and I'll show you. This is the computer in my office where I do my video editing and my software development. And here on the desk next to it, I have my electronic lead screw test bench. Now this is real electronic lead screw hardware, so this is the TI microcontroller and the interface boost board and the control panel kit, all just set up here with a breadboard so I can add additional electronics for testing. I have it hooked up to my Salier Logic Pro 16 logic analyzer, and we will make use of that in a few minutes to look at the signals and look at the issue and the solution. But I also have here on the breadboard a simulator for the encoder. Obviously in here in the house I don't have this hooked up to a lathe, so I can't spin up the spindle and test it, and that's what this is for. This is a little Arduino with code on it that simulates the quadrature output of an encoder, and that's plugged into the input of the electronic lead screw, so I can turn this potentiometer and simulate a lathe spindle. You can see right now it's reading out 61 RPM. If I grab this knob, I can turn it and increase that, and all this is doing It's just generating simulated encoder output, and I can run this all the way up to 2700 RPM, 2706 in fact. So this gives me all the range of speeds I need in order to do most of the testing I do here on the bench. So let me get a screen capture going, and let's dig in. Okay, let's start with the existing or the previous firmware, version 1.3.01. This is the one that's been published and publicly available for a few months. Let's load that first onto the microcontroller. Okay, you can see this is version 1.3.01 that's running here. And I'm running at 6100 RPM, and of course I can turn up my simulated speed to generate a faster pulse train to whatever I want. Let's stop that for a second so we can change some settings, switch over to threading, and let's go to a really coarse thread. Let's go down to 8 threads per inch. And of course the same thing happens with metric, but I'm demonstrating it here with imperial. So let me bring up logic and let's take a look at what's going on. Now, this is outputting a whole bunch of traces. The traces up here at the top are the communication with the control panel, the button reads, and the display going back and forth. And so we've got the SPI bus there. We've got some debugging traces we'll talk about in a little bit. And down here at the bottom, if I zoom way in, we have the quadrature input that's coming from the encoder. So you can see those pulses are relatively wide. If I turn up the RPM, they get narrow and closer together. Now the green trace up here is the step output to the stepper or servo. If I zoom in further, in fact, why don't I stop this? We can take a look at it. Here's a single pulse. You can see it's about 5 microseconds wide with, wide space in between, just depending on how fast we have to send the pulses to keep the stepper or servo on the lead screw in sync. So let's run this again. And as I increase the speed, you can look at the quadrature encoder on the bottom. You can see those pulses get narrower and narrower. We get more and more pulses, and the same thing is happening up here with the steps. Those are getting closer together. So this is about 500 RPM. Let's go up to around 1000. So around 1000 RPM, you can see they're even closer, and we can just keep going. I'm going to zoom in a little bit here. And you can see these pulses, as I go faster and faster, are getting closer and closer together. And if I go fast enough, we reach saturation. We're now outputting these pulses at just as fast as we possibly can output them. We can't go any faster because if we go narrower, then we exceed the specification of the stepper or the servo driver. So this is as fast as we can go, but we've actually reached saturation, so we can't go fast enough, and we're actually getting behind. So let me stop this. Let me zoom out so you can see what happens here. And I will stop the input, and the output stops. So let me back that up and zoom out so you can see what happened. So coming along here, here's where the input stopped. And you can see that the steps continued to the output. And the reason is because we got behind, we couldn't output them fast enough, and there were still steps left over after the spindle stopped. This is not a good situation because this is a case, well, first of all, we were getting out of sync because we were getting behind. But second, this is not a good situation because we've stopped the lathe, but the lead screw is continuing, and the operator is not going to expect that. In this particular case, take a rough measurement here. This was a whole 6 seconds. Now let's take a minute here and talk about what's going on. In my particular lathe, let's just pick some nice easy round numbers. Since I have a 12 thread per inch lead screw, if I were threading at 12 TPI, which is not as extreme as this case, that would be a little bit more sane, but running close to 3000 RPM, well, the servo would actually be spinning at 9000 RPM in order to spin the lead screw that fast. And this is just a nonsensical situation. Nobody's going to run a machine this fast. The person who discovered this and reported the issue to me wasn't threading this fast. They were just playing around with it and noticed this behavior. A case where they could stop or slow down the spindle and the lead screw would keep turning for a little while. So while this is not a scenario that is going to be common, it is a scenario that is possible. especially if you have a very high resolution stepper servo drive or a high gear reduction on the lead screw. It might be possible to get into this situation, so I want to fix it and make sure that this doesn't happen, both because as you're falling behind, you're messing up the thread you're trying to cut, but also because this could be an unexpected safety situation. If the operator stops the lathe and the lead screw keeps turning, that's totally unexpected, and you don't want to break anything or get hurt. So I think we should fix this, even though it's not a realistic scenario that anybody's likely to encounter. I'd rather have it fixed so that they can't encounter it. Okay, let's talk for a minute about why this happens. I've got a screenshot here from the very first video I did on the electronic lead screw, and this shows the architecture of the firmware and what's actually happening. So we have an encoder over here, that's what this circle is, that is reading the position of the spindle. That goes through a hardware counter and produces a count value, and this is the count of encoder steps that have occurred as the spindle's been rotating. That count is then multiplied by some kind of factor to get a desired position. So the desired position is in servo or stepper motor steps for the lead screw, and the count here is in pulses from the encoder. So you have your UI and you select, say, 8 threads per inch, which is what I have here. That goes through some logic to figure out what the correct multiplication factor is, so that when we take the encoder steps, multiply them by some number, we get the desired number of stepper or servo steps to drive the lead screw to the right position. And we run this continuously, and it keeps the lead screw at the correct ratio with the spindle. Now, that just gives us the desired position. Then we actually have to generate the steps. And so there's a loop, that's what these arrows are, that is continually reading the desired position, and it knows the current position, and it is driving the steps as output. So there's an interrupt loop here that's happening, and all it does is compare the desired steps to the current steps, and it generates pulses to move the current position to match the desired position. So if we go back here and look at logic, we can see this happening. Now I'm going to zoom way in here, and I've got an additional signal. Let me go back to where we had some quadrature data. So here's the quadrature input on the bottom, and here's the step output. You'll notice this other signal here that says ISR active, and ISR stands for interrupt service routine. And what I've done is, in this code, this little loop here that's running, that's trying to drive the current position to match the desired position, that's an interrupt. It wakes up every 5 microseconds to do its work. And when it wakes up, I turn a signal pin on, and when it's done, I turn that signal pin off. And so that allows me in the logic analyzer to hook a wire up to that pin, and I can see what's happening. So you can see this is running at 200 kilohertz, which is a pulse width of about 5 microseconds. So when this goes high, it means that interrupt service routine is running. It's comparing the count. It's deciding, oh, it's time to change the output signal, and in this case, it lowers it and ends a pulse. 5 microseconds later, it wakes up and it starts a new pulse. 5 microseconds later, it wakes up and stops a pulse. So let me turn the speed back down here, and let's start another capture. And so you can see when we're not at saturation, we have this case where it came along, it started the ISR and decided, oh, it's time to start a pulse, so it raised that line. Then 5 microseconds later, it ended that pulse. 5 microseconds after that, it checks the numbers to say, is the desired position the same as the current position? In this case, it decided, yep, close enough, we don't need a pulse. And then 5 microseconds later, it decided, oh, it's time for a pulse again. And so this is how the system works. And as you go faster and faster here, you can see when we're going really slow, we've got lots and lots of time between pulses. Most of these ISR hits aren't doing anything. And as we go faster and faster, these get closer and closer together. And when we eventually reach saturation, what's happening is every time the interrupt service routine wakes up, it sees that it's time for a pulse, and then the next time it wakes up, it turns that pulse off, and that gives us our 5 microsecond pulse train. Now, a good question is, why 5 microseconds? It's because 5 microseconds is the typical minimum pulse width accepted by the servo and stepper drivers that I've worked with. It would be possible to change this. You could make it go faster, but the time between when these interrupt service routines are running, this empty time, this in this case 3.7 microseconds between executions, that's when the microprocessor can do other things like service the UI. So you have to have some time between these. Plus, if you went any faster, most servo and stepper drivers would start missing pulses. So this is really as fast as we can go. So what's happening here is once we reach saturation, we're outputting 1 pulse every 10 microseconds. That's as fast as the system can go. That's 100 kilohertz. And so as this loop is running, driving the current position forward just as fast as it can go, it's not fast enough. The desired position is getting ahead. And so these two values are diverging. And eventually, when you stop counting, these numbers are still different, and the code will dutifully continue to drive the current position forward until it matches the desired position. And so in this case, where we were getting behind, let me zoom out here and find that. Oh, I don't have it here. So in this case where we're getting behind and we stop, the quadrature input stops, but that loop is still trying to drive the current position forward to match the desired position, which had gotten out of sync. And that's why this occurs. Now keep in mind, we are talking about a rare corner case here where you're overdriving the system. For most people's setups, you won't encounter this because you're not going to be trying to thread 8 threads per inch at 2700 RPM. So how do we fix this? Let's go back to the code and let me jump ahead here to version 1.4.0, which I just released. And let's program that into the microcontroller. Okay, there we go, 1.4.00. And let's take a look at the code and see what we actually did. So the first thing is in configuration.h, I added a new configuration item, which is the max buffered steps. So I'm referring to this when these get out of sync as buffered steps, because basically steps have been buffered up, and then after you stop the lathe, those buffered steps are going to continue to be output. Now, I picked a number. In reality, a number like 1 or 2 would probably be fine, but there are cases in certain configurations where it can output bursts of 2 or 3 steps at a time, just because of, especially if you have a low resolution input encoder. So I picked a large number like 100. Now, if you have trouble with false triggering, you could always increase this value. But if we're outputting at 100 kilohertz, 100 steps is 1,000th of a second. So we're talking about 1 millisecond worth of steps at the maximum output speed. So this should not get in anybody's way, and it should, and in the worst case scenario, if we do get behind, we won't be behind by more than 1 millisecond. So if you stop the lathe, everything will stop within 1 millisecond, which is plenty. So then in the main loop that's running servicing the UI, don't have it in the interrupt service routine because that has to run very quickly. But I'm actually in here coming in every time we go around the user interface loop, which is 50 times a second. I'm checking the step backlog to see if we're getting behind. And you can see the code in here is, I'm pointing with my finger, it's checking to see if desired position minus the current position, takes the absolute value of that, and if it's greater than the maximum number of buffered steps, then we disable the drive and return true. And in this case, we go to the user interface and generate a message that indicates that we have panicked and stopped. So let's take a look at what actually happens. So I've got this running now. Let me switch this over to feed thread, and let's thread at 8 threads per inch. And let's increase the speed and see what happens. So let me zoom in here so that you can see this happening in real time. And you can see we've got lots of space between the steps. And as I speed this up and speed this up, they get closer and closer and closer. And eventually we reach saturation and boom, it stops. If you look at the display, it says too fast, reset. So the way you have to fix this and get it out of this state, in this case, you can see that the steps have ceased. Even if I slow this back down, it doesn't matter. It will not restart automatically. So you can see in this case, the spindle's still turning. I still have my steps generated at the bottom. The ISR is still running, but we are no longer generating step outputs. And in fact, the enable line has also switched and it has disabled the stepper or servo driver. So you have to stop the lathe first. So let me stop the lathe, use the power switch to turn this off and turn the ELS back on. And now it has reactivated. And if I let the lathe start again, you can see now we're generating pulses. So again, all that this is doing is it's panic stopping. Now, what is the right thing to do when we start getting behind? Well, there aren't a lot of good things, because if you were actually in the middle of a cut, cutting at 8 threads per inch at 3000 RPM, and you exceeded that threshold, it would stop the lead screw and it would wreck your part and might even break your tool. It's certainly not going to be what you expected. But again, that's a really rare situation, and we're trading that off against the possibility of the lathe continuing to run after you turn it off, and that's just a safety issue. So I think the only realistic thing that we can do here, the safest thing to do, is to simply stop the electronic lead screw cold. Just panic stop it. And so that's what happens. We go faster, a little faster, a little faster, and boom, we just stop it. And so that's how this works. If you ever encounter this situation where where it stops and won't run, it says reset too fast, you know you were doing something crazy, and so you just have to stop the lathe, power cycle it, and it will come back. This new version of the code is out on the GitHub project now, and there will be a link down in the video description. And when you come to the main page, just come over here on the right where it says releases, and you can see version 1.4.00, which is the latest. And we've got a change log, and here's the source code as a zip or a tar.gz, depending on what you need for your platform. Hint, if you're on Windows, you probably want the zip. Now, there are actually two changes in here. One is what we just talked about, dealing with the maximum step rate and automatically stopping the lead screw for safety. And the second one was a change to the memory map. A few people have edited the firmware to add new thread definitions and ran into some memory problems, and this allows bridging across the econst segments, and that solves that problem. If you know what that means, then that's probably for you. Now, this code still is designed to run in Code Composer Studio version 9, because that was the initial version. That is still a supported version of Code Composer Studio, though it's not the latest. The latest is now version 10. I wanted to keep this compatible with version 9 and not do the upgrade yet, because I want to make sure that anybody who's set this up previously can easily get this new version, especially since it is, while a corner case, a safety issue. So it does actually work in Code Composer Studio version 10. If you download version 10 and load this up, I tried it this week, it worked fine for me. You do get a warning saying that it's a different version of the compiler, but it seems to work. I do have a branch in the repository with official support for CCS 10, but again, I'm not going to release it yet because I want to make sure that anybody who used 9 in the past can get this new version. Now remember that on the main page, you scroll down here, we have documentation over on the project wiki, and this has everything you need to know about wiring everything together and how to actually program the microcontroller. There's a video walking through the programming process with Code Composer Studio 9.1. And so I think everything that's needed is out there. And again, if I missed something, leave me a comment and let me know. That's all I've got for you today. This is, I know, not my usual fare, getting into the software and the electronics more, but we do that from time to time. If you enjoyed this video, give it a thumbs up. Thank you for watching.